Today we are going to be starting a new unit, Unit 5 on probability. And our first lesson is primarily on just terms and definitions and a little bit of a review of junior high probability. So let's get started. 5.1, probability, terms and notation. So before we get into some of the definitions, I just want you to take a look at these 3 questions here. So these are questions you would have done in junior high. So what you look at the scenarios and think about what your probabilities might be. So a fair die is rolled. What is the probability of rolling a 2? A circular spinner is divided into 4 equal sections. Clubs, they're labeled clubs, diamonds, hearts, and spades. And when it's spun, what is the probability that it lands on clubs? And then the last one, 2 coins are tossed and the number of heads is counted. What's the probability of obtaining 2 heads? All right, so we're rolling a die, we're spinning a spinner, and we're tossing some coins. So take a minute to pause the video, think about what your answers might be, and then as we work through this lesson, you'll see if your answers were correct. All right, so before we get into the actual examples, it's important that we look at a bunch of terminology. And a lot of this is going to relate to things that you've done in junior high. So a lot of this should be familiar, but if it's not, hopefully it will be by the end of this lesson. So first of all, probability theory deals with the mathematics of chance and prediction. And in junior high, you would have done a lot with experimental probability. You would have tossed some coins and flipped some spinners or spun some spinners, rolled some dice. But in high school, we're focusing primarily on the theoretical probabilities. So some terminology that you would have used back in junior high. We would have talked about trials. So a trial is an operation where the outcome cannot be predicted with certainty. So a coin is tossed, a die is rolled. We can calculate the theoretical probability, but the trial is when we're actually doing the experiment. And then the experiment consists of 1 or more trials. So tossing a coin 5 times or rolling a dice 6 times and so on. So that would be the experiment. Now, once you've done the experiment, the outcome is the result of carrying out the experiment. So the outcomes are what we get when we do the experiment. Now, the sample space, this is one that we're going to talk about quite a bit throughout this unit. Sample space is the set of all possible outcomes of an experiment. And so if we were tossing a coin and rolling a dice, we would have all of our possible outcomes listed. An event is a subset of the sample space. And so there could be 1 or more possible outcomes of an experiment. So we could have, after we've tossed the coin and rolled the dice, one outcome or one event might be that we get heads and a 1 and a 4, or we get a tail and a 2. Okay. Now, if we're looking at notation, if we're trying to denote the probability of an event, we write it as the probability of A. So the probability of event A is P of A, and we read it as the probability of A. Now, probabilities are usually represented by decimals or fractions between 0 and 1. There is the odd time that you're going to see it represented as percentages. So if you're doing a numerical response question, it's important that you read whether it's a decimal or a percent. But typically in high school, we're representing it as a decimal or a fraction. Now, if the event X does not include any of the outcomes in the sample space, then that event is impossible. And we would write that the probability of the event is 0. So the probability, for example, of rolling a 7 on a standard die is 0 because there's no 7s on the dice. If event I includes all of the outcomes, then it's considered a certain event and the probability of Y is 1. So for example, probability of flipping a heads or a tails using a fair coin, well, that's a certain event. We're either going to get heads or we're going to get tails. So there's a 100% chance or a 1 probability that we're going to get a heads or tails when we flip a coin. All right, so let's take a look at some example questions here. We're going to be visiting these junior high math problems as we go through the rest of the lesson. So if an event has a set of equally likely possible outcomes, then the probability of a particular event is given by the number of outcomes, so what we want, divided by the total possible. So if we're writing this down here, the probability of favorable over possible, so in other words, this is what we want, over the total possible. So if we're flipping a coin and we're looking at the probability of getting heads, well, there are two possibilities, heads or tails, and we've got a 1 out of 2 chance of getting heads. So let's consider our first scenario. A fair die is rolled, and we want to know the probability of rolling a 2. Well, we have 6 numbers on the die. The probability of getting a 2 is 1 out of 6. So we would write probability of 2 equals 1 out of 6. Now, a circular spinner is divided into 4 equal sectors, labeled clubs, diamonds, hearts, and spades. And when we spin the spinner, we want to find out what is the probability of landing on clubs. So the probability of getting clubs is 1 out of 4. Now let's look at these in a little bit more detail. So for the first example here, we want to list the sample space. Well, the sample space for a die is 1, 2, 3, 4, 5, or 6. So those are all our possible outcomes. And notice I'm writing it in set notation, or I'm writing it as a set. Now, our favorable outcomes. So what are the outcomes that we want? Well, in this case, we want a 2. Okay, you can write it as a set or just write the 2. If we look at the die, is it equally likely? Are all of the outcomes equally likely? And the question is yes. So yes, these are equally likely. A scenario where it might not be equally likely is if it wasn't a fair die, and for example, I had a 1, 2 2s, a 3, a 4, and a 5 on there. Well, then it wouldn't be equally likely because I have more than one of a number on there. And then our probability we've already listed. Probability of getting a 2 is 1 out of 6. Now let's look at the spinner and do the same questions. So first of all, our sample space. Our sample space we can write in set notation. And for this one here, it would be clubs, spades, hearts, and diamonds. Our favorable outcome, in this case, we want to get clubs. So our favorable is clubs. If we ask ourselves, is it equally likely? Well, we're looking to see, is there the same probability for every single section? And if we look, these sections are all equally divided. So yes, this is equally likely. If one section was smaller than the other sections, it would not be equally likely. And then the last one here, the probability, as we've done before, the probability of getting clubs is 1 out of 4. All right, so let's take a look at complementary events. Now, this is something you likely looked at as well in junior high, but we're going to talk about it again here. So the complement of an event, notice spelt with an E, not an I, but the complement of an event is the set of outcomes in the sample space that are not included. So if we're looking at event A, the complement of event A would be the ones that are not included. Now, the way that we denote that, we can do the probability of not A, so we can do A prime, or we can do the probability of not A bar. And you'll see both of them throughout. All right, so let's break this down. So consider the spinner from earlier. So we have our spinner here, and we want to look at the sample space. Well, first of all, our sample space is clubs, diamonds, hearts, and spades. And if we want to consider the event of landing on clubs, that has one outcome. So on our spinner, there is one section that is clubs. So the green section is clubs. So the probability of getting clubs is 1 out of 6, or sorry, 1 out of 4. 1 out of 4 there. Now, if we want to consider all of the possible ways that we don't get clubs, if we count up those sections, we would have 3 out of 4 because there's 3 sections that are not clubs out of a possible 4 sections. So the 1 out of 4 and the 3 out of 4 are complements to each other. So landing on clubs, and not landing on clubs are complementary events. Okay? And so we say that one is the complement of the other, and then we can also describe them as complementary events. Now it's important for you to note the probability of an event and the probability of complement will always add up to 1. Okay, so if we were flipping a coin, the probability of flipping heads is the event. The probability of not flipping heads would be the complement. So the union of the set of outcomes for probability of A and the set of outcomes for the complement of A will be all of the elements of the sample space. So if we think about our set theory, the probability of A or not A is going to be 1. So the probability of A plus the probability of not A is 1. We can also write that using A bar. All right, so using the die from the review, so the very first section there, we want to list the outcomes for the complement of rolling a 2. Well, if rolling a 2 is the event, then the complement would be not rolling a 2. So 1, 3, 4, 5, and 6. So that would be the outcomes if we want to look at the probability of not getting a 2. So I'm going to write it with a 2 in the bar. So probability of not getting a 2 would be 5 out of 6. So events formed from repeated trials or from a combination of simple events are called compound events. And so that's where we're looking at maybe tossing a coin and rolling a die, or spinning a spinner and flipping a coin. So some examples here: 2 coins are tossed and the number of heads is counted, or what is the probability of obtaining 2 heads? Okay, so we have repeated trials of simple events. And so it could be 2 coins, or it could be a coin and a spinner, and so on. So first example here, it says a student lists the sample spaces of 2 heads, 1 tail, and 2 tails. So they're flipping 2 coins and they list their sample space as 2 heads, 1 head and 1 tail, 2 tails, and they say that their favorable outcome is 2 heads. There are 3, and the person then says, since there are 3 elements in the sample space and only one of these is favorable, the student has concluded that the probability of obtaining 2 heads is 1 out of 3. So I want you to take a minute to pause the video and determine why this isn't right. So again, the student's sample space is up here. They're flipping 2 coins and they've listed their sample space as 2 heads, 1 head and 1 tail, and 2 tails, and their favorable outcome is 2 heads. So they've decided the probability is 1 out of 3. So try it on your own, and then we're going to talk through it here. All right, so the reason the student is not correct is because the outcomes listed are not equally likely. And so if we were to write out our sample space correctly, and we'll do that here right away, if we were to list our sample space correctly, we would realize that the 1 head and 1 tail is more likely to occur than 2 heads or 2 tails. And so one way that we can set up a sample space is to create a chart. We can also use a tree diagram. So if we want to use a tree diagram, we're going to have 2 heads. So we've got a heads and a tails. And then for the second event, we can either get a heads and a tails or a heads and a tails. And so then that leaves us with our sample space here. So we can get a heads and a heads, a heads and a tails and a head, or tails and a head and tails. So that actually gives me 4 possible outcomes. So the probability of getting a heads and a heads, is 1 out of 4. The probability of getting a tails and a tails is 1 out of 4. But the probability of getting a heads and a tails or a tails and a heads is 2 out of 4, which is 1 out of 2. All right, let's look at another experiment here. So we want to consider the experiment of spinning an equally spaced triangular spinner. So we've got our 3-section spinner here, and we're tossing 2 coins. And so I'll see if I can move this around here. So we have a spinner with 3 sections, and we're flipping 2 coins. So the first thing we're going to do is label a tree diagram. Again, this can be done with a chart, but when we have 3 events, it's better to do it as a tree diagram. So our first section, we've got a spinner. We can either get a 1, a 2, or a 3. Our first coin, we're either going to get heads and tails. And then our second coin, we're either going to get heads and tails. So we can get a 1, a heads, then a heads or tails. We can get a 2, a 1, a tails, and then a heads or a tails, and so on. So I'm going to go through and fill in the chart here. So you get a 3 and either a heads or a tails, and we can get heads or tails, and then heads or tails. Now, once you have that, it's helpful to write out your full sample space. So you can get a 1, a heads and a heads. We can get a 1, a heads and a tails. We can get a 1, a tails and a heads. We can get 1, tails and tails. We can get 2, head, head, 2, head, tail, 2, tail, head, and 2, tail, tail. And then we can get 3, head, head, 3 heads, tails, 3 tails, heads, and 3 tails, tails. So if we look at our sample space there, we have 12 possible outcomes. So it says how many elements are in the sample space? Well, our sample space has 12 elements in it. Now, how could we use the fundamental counting principle to determine the size here? Okay. So we think back to our last unit, there are 3 possibilities for the spinner. There are 2 possibilities for the first coin, and there are 2 possibilities for the third coin. So 3 times 2 times 2 is 12. So that's us using fundamental counting principle. 3 choices for the first, 2 choices for the second, 2 choices for the third. So then the next question is, are these outcomes equally likely? And the answer is yes. If we go through there, there's no repeats. So these are all equally likely. So the probability of getting a 3, we want to consider the probability of getting a 3 and 2 heads. So the probability of getting 3 heads, heads. So we look in there, the probability of getting 3 and a heads is 1 out of 12. Now, what about the probability of getting a prime number and exactly 1 tail? Well, a prime number and exactly 1 tail, just 1 sec here. The probability of getting a prime number and exactly 1 tail will include the 2s and the 3s. Remember that 1 is not prime. So we could have a 2 and a heads and a tails. We could have a 2 and a tails and a heads. We could have a 3 and a heads and a tails. Or we could have a 3 and a tails and a head. So that probability, there's 4 possible outcomes out of 12 total possibles. That reduces to 1/3. So it would be probability of prime and 1 tail would be 1/3. All right, we're going to take a look at one more example here. So we've got a blue die and a red die that are being rolled, and the outcome 2 on the blue die and the outcome 4 on the red die can be represented as 3, 4. So we're going to create a sample space this time using a chart. And so we're rolling a blue die and a red die. If this was junior high, we'd spend some time doing some experimental probability. But right now we're looking at theoretical, so we're going to write out our sample space. So we can start listing our sample space here, 1, 1, 1, 2, 1, 3. Just to make it go quicker here, I'm just going to fill in the chart. So we're going to have 1, 1 all the way down to 6, 6. So these are all the possibilities. This isn't an array or a table. And we want to ask ourselves, how many items are in the sample space? Well, if we count this all up, we have 36 possibles. Now, again, we can use fundamental counting principle. For the blue die, there are 6 possible outcomes. For the red die, there are 6 possible outcomes. And so 6 outcomes and 6 outcomes, remember, and is multiply, gives us 36. So we can use the fundamental counting principle again to figure out the size of our sample space. So part C says, list the event the same number appears on each die as a subset. All right, if we want to list this as a subset, we're going to have 1, 1, 2, 2. So essentially we're looking at the sample space getting doubles. So 3, 3, 4, 4, 5, 5, and 6, 6. So this is our sample space, and we'll always list that as a set. Now, if we want to look specifically at probability, now we're looking at our favorable over our total. So it's really important that when you're doing questions, you look to see if you're being asked for the sample space or the probability. So D says state the probability of the following events. Well, we want the same number appearing on both dice. Well, based on our sample space, that's 6 outcomes out of a possible 36. So we want the probability of doubles. So the probability of doubles is 6 out of 36, which reduces to 1 over 6. So we'll typically write these as fractions in lowest terms. The second one that says to state the probability that a different number appears on each die. Well, we can count those all up, but if we notice, the doubles are the 1, 1, 2, 2, 3, 4s, 5s, and 6s. So if those are all the times that they occur to be the same, then everything else would be the times when they occur to not be the same. So this is the complement, so we can go 1 minus 1 over 6 to get 5 over 6. So the second example here is the complement of the first. And so because one is a complement of the other, we can go 1 minus. All right, the last question says, how can the answer for D be determined for the answer for I? Well, we've just answered that. One is the complement of the other. So if we've got a sample space, we could have just counted this up and said, well, there are 30 out of 36 possibles, which reduces to 5 over 6, or we can use the complement. All right, so those are our probability questions for today. Tomorrow we're going to look at a new concept called odds, and it's a term that you're going to be new to, but it's one you've probably heard in media before. So tomorrow we're going to be looking at odds, so it's important that you have a good understanding of probability after today. All right, guys, we'll see you soon.